before we go to the new stuff, I'm going to go back to a little review of what we did yesterday. I'm going to put this line through here again. Stuff above the line is just definitions from yesterday, and then here's kind of what the transformations look like. So let's go back to transformation. Remember, a transformation is when we move a shape on the coordinate plane. That's all a transformation means, just moving the shape. There's two different types of transformations. A congruence transformation is the first one. Congruence transformation, when you move the shape does not change size. It stays the exact same. The opposite of that is what we're going to get back here on the second page, similarity transformation. There's actually two different kinds of these. Similarity transformations, the size of the shape does change when you move it. It either gets bigger or it gets smaller. We'll come back to that in a second. Now, if you remember, your congruence transformations, those are the ones that do not change. There's three types. Translation is the first one. Slide is the word you want to remember when it comes to a transformation. What we're going to do is we're going to slide it from one place on the coordinate plane to another. So here's a picture of kind of what that looks like. If you slid this over, the shape does not change at all. We just slid the picture of the shape from one side to another. Reflection, the word to remember with reflection is flip. When you do a reflection, you're going to flip the shape. So like this one here, if you take that, we flip it over, it comes to this shape right here. And then our third type of transformation is the rotation. Word to remember with rotation is turn. That's where you're going to turn the shape around the point on the coordinate plane. So like if this is the point on the coordinate plane, you can look at it two ways. We could either turn it this way, or if this was your original figure, you could turn it down to make it turn to that point there. So the first thing we will do is go to the second page. This is the first thing that'll happen on your test on Thursday or Friday. We're going to give you some pictures.
Excuse the interruption. This is Mr. Carver. We are going to be conducting an emergency lockdown drill at this time. Again, we are doing an emergency lockdown drill at this time. Thank you. Lock your doors and move to the appropriate location. Thank you.
All right, we're actually not going to move today because of COVID. So just stay right where you're at. If this was a real emergency, we would all pile up in that corner right up there. But because of COVID, we're not going to do that today. That's your emergency drill for the day. Any questions? Okay. Let's get back to what we were doing here. All right, directions are going to ask you to tell what kind of transformation this is. So we've got three different options. It can either be a translation, reflection, or rotation. Let's write that up here. And all we have to do is just look at the picture and decide which one of those that is. Which one of these three options is being shown in the picture. Now, if it helps, remember your words. Translation, what's the word to remember for translation? Slide. We're going to slide the figure to another spot. How about rotation? What word can you remember for that? Or turn. If you rotate it, you're turning it. How about reflection? Flip. Yep, that's going to be your mirror image. So if it helps to remember those, think of them that way. Then we just look at the picture. You look at your first picture here. We've got two shapes. From this first shape to the second shape, we flipped it over the x-axis. When you flip it, it's called a reflection. And that's all we have to do with that one. We just have to tell it's a reflection. Let's try the second one. What did they do to get the second one from one shape to the next? What did they do? They rotated it. They turned it. So you can either think of it as turning this way or turning this way. When we turn it, we rotate it. Makes it a rotation. How about the third option down here? What did they do? That's translation. They slid it from one spot to the other. When you get to your test on Friday, there's going to be 5 or 6 of those. And really very simple. You just have to tell whether it's reflection, rotation, or a translation. Any questions with that? Okay, now let's get to the part where there's a little bit more work to it. The next one at the bottom, they want us to identify the transformation and then verify that it is a congruence transformation. Let's start with the first part. Identify the transformation. Here's the first shape, here's the second shape. Did we slide, turn, or flip this one? That's a slide. Slide is a translation. So this would be the first part of your answer is translation. And then for the verifying part, we're going to verify it's a congruence transformation. Remember, congruence transformation, the size does not change when you move the shape. So you can see these shapes are the exact same size. What we're going to do is we're going to prove that they're the exact same size. And we're going to do that by showing that all 3 sides on each triangle end up being congruent to each other. The corresponding sides end up being congruent. Now, to do that, you have to go back to your distance formula, which you learned in algebra, and then we did a bunch of it.
Mr. Carver, this is Mr. Carver again. We are all clear on our drill. All clear on our drill today. Thank you everyone very much. Have a great day.
Distance formula, if you remember, we're going to do the square root. We're going to subtract the x coordinates first and square them. We're going to add to that the same thing with the y coordinates. Subtract the y coordinates and square them. The first time we go through this problem here, I'm going to go through each step on the distance formula. And then the next time we do it, we'll kind of do the shortcut method to it. I want you to see the long way of doing it, just so you see where it comes from. Because we haven't done distance formula in kind of a while. What we need to do with this is do this distance formula 6 different times. We've got to do it for each side on each triangle. And we're going to kind of match the sides up as we do it. So I'm going to start on this left-hand triangle with AB. I'm going to find the distance between those points that go from A to B. Now, before you do this, it might be helpful if you write down the coordinates so you can see it. Now, these numbers are really small and my eyes don't see it very well, but I think this point A, we had to go -2 to the left and up 0. That's a -2, right? Okay. -2, 0 for point A. Point B is -3. Let's say -5. Yeah. -3, -5. And point C over here is at -1, -4. And then let's do the same thing for the other shape over here. Point Q is at 3. I can't read that. It's -3, right? 3, -3. Point R is at 5, -2. And point P at the top, 4, 2. Now that we have those points written down, we can put those x and y coordinates into our distance formula. Well, let's do it for AB. I'm going to start with the x coordinates. So here's point A, here's point B. The x coordinates, we would take -2 minus -3. That's going to go in for x2 and x1. -2 minus a -3, and we're going to square that. Plus in between them, then we're going to do the y coordinates. Same thing with the y coordinates. 0 minus -5. Square it. And then we got to simplify it. Got a double negative here. We're going to make those positive. -2 plus 3 is 1. 1 squared is 1. And we're going to add to that. Double negative 0 plus 5 becomes 5. 5 squared is 25. Add those two together, you get the square root of 26. Now let's just finish off that first triangle while we're at it. Let's do side AC next. Go through the exact same process. You're going to subtract the x coordinates first, square them. Subtract the y coordinates, square them. Add them up together under the square root symbol. For AC, we'll start with our x coordinates. We've got a -2 and a -1. That's going to be -2 minus -1 squared. And add to that the y coordinates. Y coordinates are 0 and -4, so that'd be 0 minus -4. Take care of our double negatives again. -2 plus 1 is -1. -1 squared is 1. 0 plus 4 is 4. 4 squared is 16. Yeah, those two up, we're at the square root of 17. All right, last side is BC. Same exact process. We'll start with the x coordinates. -3 and -1 are your x coordinates. That gives us -3 minus -1 squared. Y coordinates, we have -5 and -4. That's -5 minus -4 squared. Bunch of double negatives again, so we'll take care of those. -3 plus 1 is -2. -2 squared is 4. -5 plus 4 is -1. -1 squared is 1. Get those up, we're at the square root of 5. We just found all 3 sets of sides on the first triangle. Now, if you wanted to, you could change these to decimals, but you really don't need to. I'm going to show you why here in a second, because we're going to match them up to the second triangle. If these are actually a congruence transformation, on the second triangle, would your lengths be the same or different than the ones you had in the first one? It should be the exact same. So let's see if that happens. We want to match it up with the sides here. AB was this left-hand side. Its matching side would be PQ. And we go through the exact same process. Subtract the x's, 4 minus 3, square it. Subtract the y's. Let's see, we're doing PQ here. That's 2 minus -3. Four minus 3 is 1. 1 squared is 1. 2 plus 3 is 5. 5 squared is 25. Add those up. That is the square root of 26. There's our first set of matching sides. We have 2 sides that are square root of 26. Now let's make sure the other sides match up. AC was the right-hand side of the triangle. Let's match that up with PR. And go through the process again. 4 minus 5 for your x coordinates. 2 minus -2 for the y coordinates. 4 minus 5 is -1. -1 squared is 1. And then double negative becomes positive. 2 plus 2 is 4. 4 squared is 16. Those two add up to the square root of 17. So our second set of sides match up with each other. Now we just need the third set of sides. The bottom side was BC. That would match up with QR. X coordinates are 3 and 5. Y coordinates are -3 and -2. Three minus 5 is -2. -2 squared is 4. And got double negative there again. -3 plus 2 is -1. -1 squared is 1. Add those up, you get the square root of 5. We just showed that all 3 sets of sides are congruent to each other. So if we go back to earlier this year, we'd be able to say these triangles are congruent by side, side, side. So we just verified here that you have 3 sets of congruent sides. That is your verification of the congruence transformation. It's kind of a bunch of work, but stuff you've done before. Nothing new for you here. Any questions with that first one? Okay, that's congruence transformations. That's where the shape does not change size. Let's go to the similarity transformation, because here the shape will change sizes. It's either going to get bigger or it's going to get smaller. The change in size is called a dilation. And your dilation, you have 2 options here. It's either an enlargement, where it gets bigger, or it's a reduction if it gets smaller. And we're going to start off the same way we did just a minute ago. We're going to determine whether we have a dilation going from A to B, whether it's an enlargement or a reduction. So we're going to take the first shape as the original shape. The letter A is the original shape. Letter B is going to be the second shape. That's going to tell us whether it got bigger or smaller. If you look at the picture on number 1, letter A is smaller, letter B is bigger. To get from A to B, we had to make it bigger, so that would be an enlargement. And then the other thing they want us to do is find the scale factor of the dilation. So we have to figure out what the scale factor is for when it got bigger or smaller. Now to do this, you're going to match it up just like you did last chapter, in chapter 7. You're going to match up a set of corresponding sides. The corresponding sides will give you that ratio, which is called the scale factor. Now to do this, you've got a couple of options here. This triangle has 3 sides. Your best bet is if you have a side that is horizontal or it's vertical, to use one of those sides, because all you have to do with those is count boxes. So this bottom side, if I count the boxes, that would be 3. And if I count the boxes on this side, that'd be 1, 2, 3, 4, 5, 6. Does that look right? 2, 4, 6, yep. And I can do the same thing on the bigger triangle. The bottom of the bigger triangle is 4 boxes long. Right-hand side is 2, 4, 8 boxes. So if it's horizontal or vertical, I can just count boxes. If you have a diagonal line like this, can I count boxes on a diagonal line? No. So if you get just nothing but diagonal lines, then you would be forced to go back and do what we did here with the distance formula. Okay, but you can avoid the distance formula if you have a horizontal or a vertical side. So always look for the horizontal or vertical side first. If you do, you can just count boxes. If you don't have a horizontal side or a vertical side, then you'll have to do the distance formula on the diagonal side. But if you can avoid that, go ahead and do it. Now, when you look at your corresponding sides, we've got 3 to 4 here. We've got 6 to 8 here. It doesn't matter which one you pick. They're both the same. I'm going to go with the 6 and the 8. Our ratio, scale factor, from one side to the other would be 6 to 8. And then you always want to put that in lowest terms. 6 and 8, you divide those by 2, gives you 3 to 4. Scale factor would be 3 to 4. That's the exact same scale factor you would get if you pick the bottom 2 sides. You get 3 to 4 there. So it doesn't matter which set of sides you pick. You just need to pick one set of corresponding sides. All right, let's try number 2. Number 2, letter A is the smaller figure, letter B is the bigger figure. So we went from a smaller figure to a bigger figure. That's going to be an enlargement. And then again, you got to pick your sets of corresponding sides. It doesn't matter which set of corresponding sides you pick. I'm going to pick the right-hand sides. This right-hand side is 3 units long. This right-hand side is 2, 4, 6, 7 units long. So my scale factor would be 3 to 7. That's all there is to it. All right, let's go to letter 3, number 3. Letter A is your bigger figure. Letter B is the smaller one. To go from A to B, we got smaller, so that's going to be a reduction. And then when I first looked at this, all I saw when I first looked at it were diagonal sides. So I thought we're going to have to do the distance formula, but we don't have to because your bottom side and the top side are both horizontal. So I'm going to just use the horizontal side, count the boxes. This one here would be 2, 4, 6 units long. On the little figure, it's going to be 3 units long. So our scale factor is 6 to 3. Once again, you want to put that in the lowest term. 6 and 3 can both be divided by 3, which gives us 2 to 1. The first figure is two times as big as the second. All right, I'm going to give you a minute to do number 4 all by yourself. See if you can get both answers. We want to know if it's an enlargement or a reduction, and we want the scale factor. Anybody need more time to finish this? All right, letter A is the bigger triangle, letter B is the smaller one. We go from A to B, we get smaller, so that's going to be a reduction. And then for your set of corresponding sides, you can use the diagonal ones if you want, but you have to do the distance formula to do that. It's going to be a lot easier if you go with the horizontal sides. This horizontal side is 4. This horizontal side is 3, so your ratio or scale factor would be 4 to 3. Any questions on how I got those two answers? Okay, last thing is on the last page of this. We have to verify that the dilation is a similarity transformation. So this time, we're going to show it's a similarity transformation, which means the size of the shape does change. We're going to go about it the same exact way, except now, instead of showing that the sides are the same length, we're going to show that the sides have a proportional set of lengths. So to do that, we go through the exact same process we did before. We have to name all these points. Point Q is at -2, no, -3. Let's say 6. -3, 6. Point P way over here is at 9. Is that 9, 9? And point R is down here at the origin, 0, 0. And let's see, point C is at 2, 2. Point B is at 1, 4. And point A, that's 5, 5, 5. We're going to do the same thing we did before. We're going to show that both sets of sides, we're going to do the distance formula for both sets of sides. Now this time I'm going to do it using the shortcut. So I'm going to start with the big triangle on the left. QR is the left-hand side of the big triangle. We're going to do our distance formula, but now instead of writing out all the x's and the y's, I'm going to kind of do it in my head. I'm going to start with the x-coordinates. We're going to subtract the x-coordinates. -3 minus 0 is -3. When I square -3, I get 9. We're going to add to that the y-coordinates. 6 and 0. If I subtract 6 minus 0, I get 6. 6 squared is 36. We add that up, we get the square root of 45. Now, once again, if I wanted to put that in the calculator and get a decimal, I could, but we don't need to. I'm going to show you why here in a second. Let's get the other sides first. The top side of that triangle is QP. Doing the distance formula on that side, x coordinates, I would have -3 minus 9, which is -12. -12 squared is 144. And the y coordinates, we have 6 minus 9, which is -3. -3 squared is 9. That adds up to the square root of 153. And the other side I need is the bottom, or P. Subtracting the x's, we have 0 minus 9, which is -9. -9 squared is 81. Get the same thing when I do the y coordinates. 0 minus 9 is -9. -9 squared is 81. Those two add up to the square root of 162. Now I'm going to do the same thing for the smaller triangle. When I do the smaller triangle, should I get the exact same numbers I get here? Nope, we're going to get something smaller. So let's do that. We'll match up the sides as we do it. Here's QR on the left. That would match up with BC. And going through the distance formula here, 1 minus 2 is -1. -1 squared is 1. 4 minus, I think I put that dot in there, didn't I? 4 minus 2 is 2. 2 squared is 4. That adds up to the square root of 5. The side that matches up with QP, let's see, QP is the top. BA would match up with that. Doing our distance formula on that. 1 minus 5 is -4. -4 squared is 16. 4 minus 5 is -1. -1 squared is 1. That one adds up to the square root of 17. And then the last one, let's see, RP is the bottom side. That's going to match up with AC. X coordinates, we have 2 minus 5, which is -3. -3 squared is 9. And 2 minus 5 is -3. -3 squared is 9. That adds up to the square root of 18. For some reason, that doesn't look right. Did I do that right? Okay. All right, now, when you look at these numbers, they don't look like they're proportional, but I'm going to show you that they are. If I do the ratio of the first set of sides, I would have the square root of 45 to the square root of 5. If I do the second ones, I'd have the square root of 153 to the square root of 17. And if I do the third side, I'd have the square root of 162 to the square root of 18. And when I put that in my calculator, I'm going to end up getting the exact same thing each time, which is going to tell me they're proportional. So I'm going to show you on my calculator what that's going to look like. Starting with this one here. Square root of 45 divided by the square root of 5. Since this is a scientific calculator, I have to be careful how I put it in. So I'm going to put in the square root of 45 first. And since it's a scientific calculator, I have to close off the parentheses there. Because that will tell my graphing calculator here, my scientific calculator, it will tell it to take the whole square root of 45 before it does anything else. Then we're going to divide that by the square root of 5. And I'm going to go ahead and close off that parentheses also. When I hit equals on there, I'm going to get 3. Square root of 45 divided by the square root of 5 is 3. I'm going to do it for the other two also. Square root of 153. Close off that parentheses. Divide it by the square root of 17. When I hit that, I also get 3. And then this one, square root of 162. Close off the 162, divide it by the square root of 18. That also gives me 3. I just showed that all 3 sets of sides have the exact same ratio, 3 or 3 to 1. That makes those sides proportional. So I can say by side similarity that these triangles are similar to each other. So when it comes to your test, you're going to have to show all of these sets of sides. Then you're going to have to show that they all have the same ratio. Basically do it just like we did that. All right, did we lose anybody along the way here? Okay, are we good with the distance formula? Anybody need to see more distance formula? Have enough? Okay. All right, today, the rest of the time, you're going to have to work on an ALEKS assignment. And under ALEKS, under the assignments, I think it's called transformation. There's just 6 problems to that. It won't take you a whole lot of time to do that. When you finish, you can also bring this back, the notes. These are your notes for the translation unit, the transformation unit. We'll put that in the grade book today. The rest of the time is yours.